this lecture I will talk about the quantum error correction conditions and how some small codes, bosonic codes, satisfy these conditions for some relevant errors or do not satisfy these conditions. And I'd like to do that because that gives you, the introduction to these small bosonic codes, because both codes have been realized in the lab last few years. So that's sort of progress. But there's also some caveats for using these codes, and it leads me to say, into the sort of discussion on stabilizer codes. I gotten some feedback yesterday that some of the things I went a little too fast, because that's the risk of also using slides. So I hope to actually start with also doing something on the board as well. Another comment is that I've updated the lecture notes, and in the first part I hopefully clarified a little bit of what I meant to say about the full tolerance of the swap gate. So there's a new comments and things said on the notes that you can check out. Okay, so let's get started with, let me just state first what are the quantum error correction conditions. So, if I'm using bars, usually, this is common language, to denote logical things. And what it means is that I can have a state that lives in the code space is denoted by some psi bar of rho bar. A logical, if I encode a qubit and I do a z operator on it, a phase flip, I write it as z bar and so on. So that's sort of standard notation. And we have a set of errors, and I've discussed last lecture also how we get these errors from some Lindblad equation or some other model, or is it a toy model. And these errors are obtained from some map, some super operator. These are these Krauss operators EI. So there's a set of errors. I don't know where there's a dash shows E1, E2, etc. Right? And that's the errors that we want to correct against. And we basically want to reverse this map. Now I think that's what's interesting about quantum error correction, is that if you would have asked maybe people before this theory came about, can you reverse, noise? You say, no, of course you can't reverse noise. It adds entropy, right? And but so you can reverse it under certain conditions, and that's what these quantum error correction capture, is that the following. So you have a state in your code space, and a code space you can think about. You just have some Hilbert space of n qubits, and you're selecting some subspace and say it's two-dimensional, and say it encodes a qubit, right? It's just a subspace. So you have a state in that small subspace. Apply the map S, some noise happens, and we want to know whether there is a reversal operator, a reversal map, and that reversal map should be physically executable. It should be trace preserving, and I'll give you what it looks like, assuming if you satisfy the error correction conditions for these family of errors EI. So what we want is that starting from rho, you do this S, and then the reversal maps you back to rho. The fact that here's a proportionality you should kind of ignore, because because S of rho does not need to be trace preserving. It's just actually just characterizes a set of errors. But the idea is you really just map back onto rho when you started with rho. And there exists such a map if and only if, so necessary and sufficient condition, the following is true. Now first we need to define a projector onto the code space. So what this means is that if I encode a qubit, I just have I just have two basis states. I call them 0 and 1. I put bars in front over them because they are the logical 0 and 1. It is not just the qubit being in 0. It's it's just a label, and this projector onto the code space is equal to that in this case. And so if I encode more qubits, it's some sum over some bit strings k, yeah, whatever, however many qubits I encode. Okay, so what do we need to have is that I have to have for all I and j. So here I can be equal to j, but it can also be not equal. I put that and I put the projector onto the code space in front, and after it, this should be equal to some matrix alpha ij. This is Hermitian times the projector onto the code space. Okay, now we would like to get a little bit of intuition of what this equation means, and we'll get that also by deriving some properties of it. But one thing you can also do, you can rewrite this to say, well, okay, this is a projector onto the code space. Now I come from the left with the operator, or with the state L, and I come from the right with the state operator K. Let's say, then what do I get? So I have this equation. I come from the left with L, come from the right with K. Then this projector doesn't do anything, and I just get this, and it equals this. So that's another way of writing this error correction condition. Okay, so now what I'd like to show on the board, after one more sort of exercise step, is how one direction of this condition, meaning that if such a thing is true, what does the reversal look like? Right? So the other direction is that if there is a reversal, then such a thing must be true. Right? I'm not going to show you that. And this proof you can find in the book Nielsen and Twang in a fairly clear way, because I'm actually just using the derivation that's given there. Okay, but so in order to show you this reversal, I wanted to do one more step. And it's also sort of a relevant comment, because you say, okay, I have a set of errors EI. And what is nice about these error correction conditions is that if those satisfy these conditions, then any linear combination of errors actually satisfies those conditions. And this is also why if you can correct, a single qubit X, Y, or Z errors, you can correct any linear combination of them. So that's of course relevant, because we don't just have X, Y, or Z errors, we have linear combinations of them. But so what you could do, you could take a linear combination, which is a unitary linear combination. So I define some Fm, which is a unitary combination of these Ej. And this unitary is chosen such that it diagonalizes the matrix alpha, which I defined on the previous slide. So this is a diagonal thing. And it's a very simple exercise. It's just a one-line thing to examine this quantity, PC Fn dagger Fm PC, and then write Fm and n in terms of these unitaries and the e's. Use this to show that you get something like this. So basically the Fm satisfies the quantum error correction conditions when EI does. And you for those Fm, the quantum error correction condition looks like this, where this is now diagonal. And this is the thing, the fact that this exists, we will use to reverse the error. And one other thing is that I'm actually not covering this, is that the I gave you the EJs as part of a super operator. But these cross operators of a super-operator are not unique. You can actually do a unitary transformation of them so that you get the FMs and they realize the same super-operator. I'm not showing you that, but we can reverse that super-operator basically. Okay, so now the point is to show you this, to show you what the reversal looks like based on this this condition. Are there any questions on this? Yeah.
So just a question. Can I interpret this condition as saying that, for example, you have a state that is corrupted by a certain type of I, and then another state corrupted by a certain type of error j, and such that this is orthogonal? So that somehow that you can sort of distinguish a state that is corrupted by different type of errors. Can I interpret it?
Well, yes, but I think actually my proof of what you of the thing will make this even more clear, because we have different types of errors, how they act, and we have different types of states. I mean, clearly, yeah. So let me just elaborate on this. I think that this is wet. Okay. Okay, so what we do is that we assume that for all n and m this is true. Yeah. And I'm going to consider, I'm just going to do some rewrite. I'm going to consider this operator, FNPC, just a matrix. And I'm going to make a polar decomposition. What's a polar decomposition of a matrix? I write the matrix as a unitary times a matrix J, and J is just the square root of A dagger A. Okay, so I can apply this to this. This matrix depends on n, so this unitary depends on n. And then I just have to take the dagger of this, the square root, and then the dagger of this times itself. So I have PC dagger, Fn dagger, Fn PC. Now, PC is a projector, so the dagger is itself. Okay. What I have here is PC Fn dagger Fn PC, and actually that is just what I have here as well if n is equal to m, right? So I can put in what that value is, that is equal to dnn PC. Okay. So this is equal to un dnn times PC, the square, yeah, PC. Okay, so that's an important line, and I can interpret it. Let me just add one line. If I just, come to the right now with a cat k, and I just interpret what it means, so that it just means that Fn on a code word k is equal to un square root of dnn k. Okay, so this is the first important conclusion that we can derive from having satisfied these conditions, namely this. I have a code word k, I have an error Fn, and its effect on the code word is a unitary transformation times some prefactor. And that's a very important point, that it's a unitary transformation, because a unitary transformation will not, if I do this, if I have a state L and the same error, it will not change this inner product. It will not distort the code space. So the effect of the error n, so if I have the code space, let's call that C, and the effect of the error Fn is a new space, let's call that Cn, and what was orthogonal here will be orthogonal there. Right? So that's an important thing. Okay, but now another fact which is true for which we can find from the error correction conditions, and it also uses this. So we can just look at this quantity. Okay, so Fn PC, and then we do. No, wait a minute. I want to do this one. Oh yeah, now I interchanged the F and the M, but it doesn't matter that much. Let's look at this object. So I'm now looking at M is not equal to N. Now this one, I know what it looks like there. I interchanged the N and the M, but when N is unequal to M, it doesn't matter. This is diagonal matrix, so that should be 0. And again, I can use this line here. So let me just insert it. So I have the NN, the MM, and this unitary. So PC UM dagger UN PC. So that's 0. Okay, again, I can come from the left with some cat and from the right with some bra. And so what this means is that cat K U M dagger U N L is 0. Right? For any K and L. So what it means is that if m is unequal to n, I have this unitary, this is proportional, Fn is proportional to a unitary. So I can say, well, where am I going when I have a different error? And what this proves is that I'm mapped onto an orthogonal space. Right? So there is a different sort of copy of this code space I can call Cm. And these two spaces are orthogonal. This is why I'm drawing this as two blobs. Yeah, so what happens, what's the action of the errors? It's to basically effectively on the code space, they do a unitary transformation and two different errors map you onto two different spaces. So then it may be clear, what you do to undo the error, right? You just want to figure out on what space, which space you're mapped onto. And then once you know what space you're mapped onto, you say, well, I just do the unitary transforming me back. Now maybe the set of errors doesn't, this is subspace of the total space. So maybe the subset of errors maps you not onto any, it doesn't cover the whole space. So you do a measurement which you also say, you do a projective measurement saying, okay, am I here, 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 or, something else. But no error will send you there because, that could be a set of errors that does that. So you never get that outcome. So the recovery is essentially this map. So if we define, so let's just sort of finish this up. So if we define, so I have the projector PC on the code space. Now I can define the projector onto the kth error space. So this is the projector onto code space. This is the projector onto one of these error spaces. And I know pk is orthogonal to pl and so on. So the recovery is essentially this. Okay, so let's say we assume that pk is the identity, but if it's not, add another projector, that makes it the identity. But that's, it's when the errors don't really map you onto any, don't fill up the whole space. So then the reversal is this. Okay, take the density matrix that you currently have, do a projection of measurements, projecting it onto one of these error spaces, and then inverse by doing UK dagger, right? Yeah. So the thing is, there is so there are two features of it. One is that the error doesn't distort, like I said, there's distortion. If there's these are states orthogonal or they have some interproduct, that should be the same there. The other one is that they map onto orthogonal spaces. And the fact that they map onto orthogonal spaces comes from using a set of errors that has this thing diagonal, right? So it's not a necessity. It's something you could start with errors for which it's not diagonal, but you can always choose a basis in which that's diagonal. Okay. So I'm not going to prove this the other way because I think it's less insightful for what I'm going to talk about next. Does anybody have a question about this? Yeah.
So what's the difference between P of K and...
So pk, yeah, here. Yeah, the k shouldn't be, it's peak. It's just a different space, right? It's just a unitary. Is anybody else? Okay, so I think that gives you some intuition. And so now maybe this shows you why I focused on these super operators, because they gives you this this set of Krauss operators. So now we can say, well, I have a set of operators, and like I have this I have a bunch of this error set, and do they, can I satisfy, I have a code space, do they satisfy the error correction conditions? And the interesting thing, and this is especially relevant for bosonic codes, it will typically not be the case that this is exactly true, right? So your code can be something that it's this plus a little something, right? Something that is a higher order in your error rate. And I think that's, that those codes are also very relevant because they show that you are probably getting an improvement, but it's of course not perfect. You can do an approximate recovery. Now the thing is that, so if you meet the error correction conditions exactly, there is a perfect recovery. And there is a thing that if you meet the quantum error correction conditions only approximately for a set of errors, there is an approximate recovery. And then there is more, and we've explored this in one of the papers, there's various approximate recoveries depending on what you optimize. So I'm not going to go into that, but there's, you can do different optimization. You can go numerically, you can go analytically, but it's not a unique thing, because it's only approximate. Okay, so let's look at some bosonic code examples. Okay, just sort of too many things here. Okay, so the error set is the following. So we have a boson, you have one bosonic mode, okay, and the error set is either identity, which is basically no error, or A. Yeah. Okay, so now I have to, those are the two errors, the I and so I just have to look at, these types of inner products. So and then the code I choose is this. So this is the smallest of a class of codes. They're called binomial codes. If you want to know more, but this is the sort of the baby one. And the 0 is the Fock state with 2 photons. And 1 is if another superposition of 2 Fock states, one with 0 photons, so with a vacuum, and the other one with 4 photons. And now we can verify, and what should be the, why do I meet these quantum error correction conditions? Okay, so we can do this. Now let's say one of them says, okay, take the error and its dagger, and then, see what it's, let me look at the, okay, so let's look at these, this thing. So if L is K, and I have EI dagger, EI dagger, EI, then this should not depend on what L it is, right? This is important that this is an alpha. If you say, well, this is alpha ij, so here we take L as K, so this is out. So this is just some alpha ij, and the important thing is that it doesn't depend on, whether I have L or K. Okay, so what does this mean in this context? It means that the photon number expectation is the same for 0 as for 1. And that's definitely true, right? The average number of photons is 2 in both states. Okay. The other thing, the other condition, if the two states are different, so let's go back. So L is not equal to K. I have I is J, same error happens. So they should be sent to orthogonal states. They remain orthogonal, right? I have 2 orthogonal states, an error happens, they have to remain orthogonal. That's one of the conditions. And that's this thing. Right? So why do they remain orthogonal? Well, when you lose a photon here, it's 1, and when you lose a photon there, it's definitely is not 1. It has support on other Fock states. Right? Okay, yeah.
Does that mean that your evolution, your unitary stays unitary over this one that stays like orthogonal again?
Sorry, the unitary?
Like the unitary, that the time evolution that is evolving stays unitary, that even.
Well, I'm not doing any evolution, right? I'm just saying I have a set of errors, and where these errors come, they come from some stochastic evolution, some noise that's added to state. And these types of noise I discussed before, we're going to come back to them. We looked at superoperators in which two possible events happened. With some rate gamma, there was a photon loss, and with some, and there was also a chance for no photon loss. So, and the chance for no photon loss was not really the identity, but now I'm taking an approximation. Instead of taking these two operators, I'm taking this one. Yeah. So what the point then is that you say, well, do I meet the quantum error correction condition for this pair? Yeah, that's a different question as meeting the quantum error. And so if I meet the quantum error correction condition for this pair, then that channel can be reversed, right? That's what it says. But this, but now what we're only verifying is this channel can be reversed, but this channel is not trace preserving. So it's, it's an approximation. Yeah. Okay. So. Well, okay, again, so the other one, because this is the identity, the other conditions where I is unequal to j is simple, because one is the identity, and you get conditions like this. If you lose a photon from 0, you get to a different space, right? So the idea is that, one other way of saying is that here you're on a state space where the number of photons is 0 mod 4. And you're mapping onto a space where the number of photons is not 0 mod 4. So there are orthogonal spaces, illustrating this concept of mapping onto orthogonal spaces. Okay, so you have this thing. And so, but like I said in my answer to this question, if you look at what you really have for photon loss, a very short time, right? This was only an approximation to a sort of longer time map. So you have something like this. E1 is square root of gamma A, but E0, you have this, and we call this little back action. This is sort of, if no photon is lost, you still have an effect on the on the state, because which is characterized by this. And then if you say, okay, now let me check whether I meet the quantum error correction conditions for this pair, it's actually not true. So you get a correction, which depends on gamma. So if we do this, so if I apply the, so why is this, okay, so if I apply this, apply my E0 dagger E0, and squeeze it with my 0, and this should be the same as this expectation with the 1. That's one of the conditions. Okay, so I can write my E0 in terms of two things. So one is a term proportional to identity, another term is proportional to A dagger A, and then something proportional to A dagger A squared, right? Well, the term identity, of course, is the same here for both. The term proportional to A dagger A is also the same because it follows from this stuff, right? The number of photons is the same, but the expectation of the operator n squared is not the same, right? Because there's variance. This is not a photon number state. There is some variance in the photon number. And so this thing will be of order gamma squared, because it's the term where it goes like A dagger A squared, and one has to look at this quantity. And this is clearly 2 in this case, but it's not equal to 2 in the other case. So the point is that you could meet. So you say you meet the quantum error corrections conditions only approximately for this set. So it means that if you're looking at the process where I apply this map, I do the best recovery possible. I apply the map, do the best recovery possible, repeat this. Gradually, the fidelity of my initial state will go down. I'll have some, I will not completely correct my error. Yeah.
Do we assume that these cross operators form a complete set, meaning that sum over EI dagger EI is identical?
Yes, but okay, so I am a little bit being sloppy here because this is not true for this set, so this should be only approximate. But then you can say, well, but then the approximation, is that not canceling this thing, because the approximation is indeed of order gamma squared. So that's not, okay, so okay, I'm not doing this very, but I think there's still a distortion. Okay, so that's not,
If you consider all the high order terms, you still get a distortion.
right. There still is a distortion. in this for this set, because you, yeah. Okay, yeah, I mean, I agree with that point. Maybe I can change the slides afterwards. Yeah.
So about
Yeah.
this monomer the condition that you mentioned, so do we assume that there is only one single error event, or?
No, so the point about this super operator, if I have this, you know, S of rho is the sum over EI rho EI dagger, what this means is that, you know, you have events EI happening with some probability. Well, it's not a probability, it's just,
Yeah, but we don't
here.
get like.
We don't know which one happened.
But we don't consider like S of rho, something like
Yes, so what I assume in this model is sort of like this type of process. So I have an perfectly encoded state. I have S happening. Then I have the best possible reversal. So the, you know, the one, and then maybe I have S happening again, best possible reversal, etc. Yeah. But of course the point, also the point that I want to come later, is that this reversal is also not perfect, right? So this model is only an approximation, but it gives you, you know, idea of what kind of codes you want to construct by looking at, you know, this noise map. Okay. Yeah. So there's a nice, and this is so this is a single mode, and there's actually a very nice trick. That was so these bosonic codes are not entirely new. So the earliest investigation were by Chuang-Long and Yamamoto in '96 already, and they had a two-mode version of this code, where the average photon number is 4, so 0 is superposition of this and 1 is that. And now if you now look at the following error set, you always have to be specific, like what are your errors, because I can easily come up with variants which are, you know, different things. But now we say, okay, we have possibility of photon loss for mode 1 or for mode 2, or no photon loss for either. And here you see I've now put in a different, you know, if I expand this, because gamma is small, it's 1 minus a half, you know, and 1 plus n2, it's what I had in the previous slide. So these are all, you know, approximations of the, and again, this is not, you know, this is not the trace preserving map because of these higher order gamma things. But the reason I write it is just sort of simple to see if you can say, well, what was the problem before is when you had this no error. So I mean, one way of looking at this guy, if you do E0 on this guy, and then maybe you exponentiate it just gives you, you know, the same state. But if you use E0 on this state, it changes the state, right? Because A dagger A is, you know, 0 for this one, and it's not 0 for that. So it's no longer a superposition of 0 and 4, but it's a distorted state. And this is part of the problem. And if you do this for this thing, so now I do this error, this E0, I do it on this, and you can verify, because I now have N1 plus N2, that's always, you know, that's 4 here, it's 4 there, and it's also 4 there, right? So it gives you just the prefactor, it doesn't distort the state. So if I look at a, you know, something like E0 dagger E0 on 0, 0, that's just this prefactor, and it's the same as E0 dagger E0 on 1, 1. Because this E0 just puts you, gives you this prefactor in front of it. And it's the same prefactor. So, what?
Are these the actual errors that actually happen? I mean, are these realistic? Because you pick these sets to be anything you want.
No. I mean, that's the reason for my previous lecture that I said you have to, where your error come from. For a bosonic mode, photon loss is a dominant source of errors. Now, what you like is to say, I have a little photon loss happen, and then I do a reversal operator. All right? And so therefore I can, maybe if it's really the rate is low, I can say my error operators are approximately these. Yeah? But of course, if you let the photon loss happen for more, you lose, you know, that's the point. So you lose, you know, 3 photons. So you have a to the third. So then this type of code will not necessarily be good because it doesn't meet the quantum error correction for a to the third. And this is why this binomial code, there's a more general family in which you can correct, a to the L, and also a to the dagger to the K, and a dagger a to the M. So there's a whole family of codes that you can build, and also a cat code I'll show you, that that use more photons overall, because these are just very low photon number, but they can correct more errors in principle. Okay, another question. Yeah.
So let's say you did have distortion, like in the previous example. You can still correct it with some probability, right? If you're
No,
not trace preserving.
No, if you have distortion, it's really an if and only if. There only exists a reversal to the code space if you meet the quantum error correction conditions. This is why I think it's a very useful. So you do not meet the quantum error correction conditions. It means you cannot retrieve that information. There's always an error.
But if I drop the trace preserving condition on R.
Oh yeah. Oh, sorry. Yeah, but I mean that's post-selecting, right? I mean, you can, but it's not. What? Sorry.
With some probability I can correct the error.
Yes, I mean that's fine. It is sort of like you can do that. But the thing, of course, these methods of post-selecting are never scalable. There are short, there are bandages. Like I mean, there are ways to, yeah. Okay. So another code. So this was the sort of baby binomial code discussed, and that's been done in an experiment by, well, I don't know the author's name, it's just a bunch of Chinese researchers together with Steve Gervin, I think. It's sort of like a good summary. Cuneo is also on the paper, right? Is that true? I don't know who is on the paper.
You mean the Parity code?
No, this the smallest binomial code. This on the superconducting qubits.
The Marios and and also with
Okay, no, but it's not the cat code.
not the cat code was earlier.
Yeah, the cat code was earlier. Okay, I don't remember who's on the paper, but this has been done in superconducting. They have tried to implement this. But then, of course, you have to also discuss what this reversal is, which I'll do a little bit now. Okay, so there are also cat codes, and the smallest non-trivial member of this cat code family is what's called a four-legged cat code, and we write four-legged because 0 is proportional, I'm dropping the normalization, to a superposition of 4 coherent states. And I've drawn this sort of as blobs in phase space, meaning that where each coherent state has its support in phase space, alpha minus alpha minus I alpha. This is not a Wigner function of the state, because the Wigner function has interference patterns. And one is similar, but it has these minus signs. Now actually, so checking, you have to, this cat code you want to use also with low photon number. And for low photon number, coherent states are not exactly orthogonal. So that's actually, you have to be, not assume that things are orthogonal, but you can still verify that this is orthogonal with a bit of work, which is not trivial. I mean, I don't think you can, it's not so obvious, but okay, but what I want to talk about is the perspective. Okay, so now we can again look at this error set, so this very simple thing. Okay, and I want to say a few things about this code, which also apply to the previous code, and which I think gives a nice sort of perspective of how you want to generate the code, because the point is that A should map you into orthogonal space, right? So the so you'd like to, well, so you'd like to encode with respect to photon number or photon parity number, and one very useful operator is the photon parity operator, and that's this one, right? So this is an operator, it's a unitary operator, and if n is even, then this has eigenvalue +1, and if n is odd, it is eigenvalue -1. Right? It's these two eigenvalues on these two spaces. Now, one thing you can verify, so you can ask these two states, what is their photon parity? Right? What is their, what's their photon number, what's their photon parity, and so on. And so, oh no, this is just a pencil. So we could do that. So we can just do something like this, e to the I pi a dagger a on alpha. And so I write out, in order to know what this is, I just write out what the coherent state is. Alpha to the n, square root of n factorial, e to the I pi a dagger a on n. Right? This is just writing what the coherent state is. And now I can let this operator act on this n. I just replace this by n. And you see that this gives a, so this n, this e to the I pi n, which is -1 to the power n, I can absorb with the alpha. And so if I do that, I just get minus alpha. Okay? So what this photon, so you can verify that. And so by that token, and you could also do this for I alpha, and of course with I alpha you get minus I alpha. The fact that you have an I here doesn't change this argument. So you can, so if you apply that then to this total state, what happens is that, alpha gets mapped onto minus alpha gets mapped onto alpha, so these state interchange, and these two interchange, and so you're a +1 eigenstate of this whole operator. Right, is that clear? And the same for this, right? Because I just interchange these two and I interchange these two, I'm still a +1 state. Yeah, so both states have even photon number, even parity. So you could think about that if you're familiar with stabilizer codes or surface code, you can think about that as a check operator. The code space is such that the photon number parity is even, right? So if I measure that operator, and I find it's -1, I know I'm out of the code space. And what can move me out of the code space? Of course, if I lose a photon, it changes the parity, right? So that's a very simple way of thinking. I say, okay, if my photon, if A happens, then I change my photon number parity. I just measure that, I detect it, and I, put it back into the code space. Okay, so now another thing is this. Because the states are also distinguished by not parity, but if I go to parity, photon number mod 4, so this was photon number mod 2, and the same thing I can do with this type of stuff, and if you put that in here, so here now I have a pi over 2. And so I get an I here, right? So this is mapped onto I alpha. Yeah, so now what you can see, if you verify that 0, because all these things come with a plus, this is an eigenstate of this parity operator, the photon number modulo 4. It's a +1 eigenstate. And this is a -1 eigenstate of this operator. The photon number is 2 mod 4. Okay. And you can see that operator you can also see as a z operator, because the z, if I call this 0, and this is 0 and that's 1, the z, by definition, it has +1 eigenvalue for 0 and -1 eigenvalue for 1. So that's nice. I got my logical z as a sort of a fairly simple operator, at least. This is not some kind of weird operator. Okay, so let me now so let me now start checking the quantum error correction conditions, right? Okay, so what do I need to check? I have this type of thing. So this happens to be 0. So maybe I should. So if I start with the state 0, I had, the parity was, 0 mod 4, and so now it's, 3 mod 4. And if I start with 1, I have 1 mod 4. And clearly, of course, if I start with 0 and I apply A, it's orthogonal to 0. And the same thing for that. So that's good, right? That's one of the error correction conditions. Now I also can check if this state is different from that. So the condition was just that this has to be the same. It happens to be 0 in my case. These things have to be 0. So again, if I start with 1 and I apply A, I will have parity 1 mod 4, which is definitely different from parity 0 mod 4. Right? So these are the orthogonal spaces. So this is also the case. And if I lose, so now I can also check this condition. If I apply A here and also AP on the other side, this is also 0, right? Because of this features. Now, okay, so but that's not all the conditions yet. There's also this guy. Right, that was simple in this binomial code. This was the average photon number of the two states. And when I first thought about this code, this was for my review, I thought, I looked at what does this meet the quantum error correction condition, and so I don't see this actually happening. I thought about the code slightly different, but now if alpha is very large, you can meet this. Because then you just say, well, okay, so if alpha is very large, all these states are orthogonal, so the inner products don't matter. And right, if I take an expectation value of n with respect to the states, minus alpha n, alpha does not, doesn't do anything, or is not a contribution. And so then the average number of photons in both states is just absolute value of alpha squared, or alpha squared. Alpha is real here. So, so for large alpha, this is this definitely, you meet the quantum error correction conditions, but that's not really at the right limit, because for large alpha, the approximation, I said the error operators are identity or A. And why could I do that? Well, really what I have physically is the identity minus this back action part. And that depends on the number of photons, and gamma is small, but if n is huge, this approximation is not really valid, right? So the point is that your loss rate is very small, but you still lose a lot of photons because you start with many photons, right? You have many photons. And if you have many photons, then this is a big distortion on the code space potentially. And now there is this amazing thing. I think it's good. When I first learned this, actually, I thought this was not working, but then my postdoc actually showed this, and also in the Yale group they realized the same, that there is but this was not in the original paper where this code was proposed, there is a sweet spot which is defined by this condition, we say, well, where does this come from, that actually you meet the quantum error correction conditions for this. And this comes, and the sweet spot, the smallest version of this alpha for which this equation is true. So the tangent hyperbolic you can think about as being dominated. It's kind of large enough alpha, it goes to -1 because it's sine divided by cosine, so either the x only matters, either the minus x is very small, so it's kind of -1. And so this is the -1 line, and this tangent hyperbolic is something like that. So there's actually multiple crossings for this alpha. And the smallest one is at this point. And this is actually this experiment on the cat code. I don't know if this is all on purpose, but it is right at this spot. They didn't want to choose an alpha that's very large because, that's harder to handle, and well, it doesn't make the code better. And it's right at this value. Yeah, so there's one can do an exercise. I didn't make this a formal exercise. Here I actually give, if you want to read more about it, I give the normalization of the state, and you can see, if I say what's the average photon number in these two states should be the same, what's the condition then on alpha, using the inner product between two coherent states alpha and beta, you could verify this. Now, one thing maybe this is not so. So we did a little plot, but maybe I can go through this just briefly. So the type of scenario we look at in this way is where you say, well, you know, if this quantum error correction, so you have a qubit, you encode it perfectly. That becomes the encoded qubit. We're assuming no errors here, but this is just a model to, you know, to model things. Now I have a channel S gamma, which has these error operators E0 and E1, with also the distortion, but I apply it for some time t, and then I have a reversal which is perfect, and then I decode, and then you get something. Maybe I shouldn't actually, yeah. Okay, I don't want to actually cover this right now, so maybe I shouldn't have engaged in this. Okay, yeah. Sorry, what? Yeah, the different curves are different. See, the thing is, you can say, well, I can vary t here. So if t is longer, I have the chance of having more photon losses, and I can't correct it. So this is sort of a lifetime of my qubits should be small, but it kind of blows up at this sweet spot. It gets very large. So these different color curves are different t, and here this is the measure of the average photon number. Okay, but I actually don't. Maybe I don't want to go into this. Now, what I want to say. How am I doing on time? Half an hour. Okay, fine. Yeah. So okay. So I have 2 slides on this part, and then I want to talk about stabilizer codes. So we said there exists a reversal operator, right? And the reversal is this. In principle, if you meet the quantum error corrections exactly, it's given by this projection and then the unitary. Yeah? But now we have to imagine that we actually do this, which is not necessarily easy, or maybe this projection, introduces more errors than it takes away, or it introduces different types of errors. And this is, I think, one of the hard parts of using these codes. And in that sense, the CAT code has nice features, because sort of separate from whether it satisfies the quantum error correction conditions, you can intuitively understand that measuring photon parity is a way to do some correction. Yeah? Because the codes, then you kind of measure whether you're in this original space or in some orthogonal space. And you would like to make sure that when you do this measuring of photon parity, you're not measuring photon parity mod 4, right? Because then, or you're not measuring the photon number parity mod 4, because that distinguishes 0 from 1. And you don't want to, right? If you do a measurement that says, oh, we're 0 or 1, you've destroyed your quantum information. So, okay, so if you have an operator, like the photon parity operator, this is just some unitary operator. And I care about whether it has plus or 1, it has plus or 1 eigenvalues plus or minus 1. And for such an operator, just a simple circuit, which I could also, if P is a Pauli, which has minus 1 plus 1 eigenvalue, I do the same circuit, and it's this circuit. I take the state, which is my oscillator in this case. I take an ancilla, which is in a qubit in a plus state, and I do controlled P, and I measure the qubit in the plus minus spaces. And it's a very simple exercise to show that if you find plus, you've projected the state on the plus 1 eigenspace. If you find minus, you have projected the state onto the minus 1 eigenspace. So this is the way you also do, if like I said, if this is a Pauli, this is also the way you do stabilizer error correction, where you have ancillas that help you to do these projective measurements. Right? Because, so the point is that here you'd say, okay, I have to do this projection pk. It's of course nice if there's a simple circuit that allows me to do this projection. That circuit involves some ancilla and some simple physical operations. And in this case, what we need to do is controlled e to the I pi a dagger a. And so if the qubit is in 0, we don't apply this. If the qubit is in 1, we have to do this. And this is naturally given if I have an interaction in the Hamiltonian that looks like this. You know, it's if the qubit is in state 1 times a dagger a, right? So then if the qubit is in state 1, it rotates this bosonic mode. If the qubit is in 0, it doesn't rotate in this bosonic mode. And this is precisely the interaction that you have if you couple like a transmon qubit off resonantly to a resonator. You have an effective interaction that looks like this. And this is why this is, and then you'd like to turn this interaction on for a little while such that you have this, you know, pi rotation that's accumulated. Yeah.
Sorry, I just really explain one question. How do we spot the error here?
I'm not saying what is the recovery, but I'm saying, let's say you want to know, well, this is one way of detecting or correcting photon loss. See, the point is that if you say, first you have to say, do I meet the quantum error correction conditions? No, then there's no perfect recovery. Okay, so that we can do all kinds of things, but there's none. If we approximately meet the quantum error correction conditions, we say, well, what was the best way to do? Or what's maybe the simplest way to do? And one very simple thing, which works very well, which they've done in practice, is to do this. And to do this repeatedly. So, you know, you have your state, you do this measurement, and you keep on doing it. And every time you say, okay, you know, does the photon parity switch, yes or no? And you assume that that measurement is reliable. Of course, if it's not reliable, then, you know, there's, so the point is of that experiment, so this is a very nice paper by Ofek et al. For the Yale group. And the thing is that one of the bigger issues was that you know, this qubit is not perfect too, right? So this qubit, instead of being a superposition of 0 and 1, it can decay. Now what happens if it decays during this, you know, controlled rotation? Of course, if it's in 0, it doesn't do the rotation. If it's in 1, it does the rotation. And let's say it decays halfway. Okay? So let's say that, you know, first here in this thing, it's like controlled p instead gives you controlled p to the alpha with alpha less than 1. It does, if it decays sometime, you know, during this evolution, you get less rotation if you're in the one state. But if it decays halfway, then you can, you know, this is just an example, by mistake, just apply controlled p to the half, right? And if what was p to the half? Well, that was e to the I pi a dagger a over 2. So that was the logical z. So actually, in that case, that's just one error event, right? When it decays exactly halfway, you're measuring the eigenvalue of the logical z, which is not at all what you want to do, right? So the problem is that if the qubit is no good, you know, the point is that, well, we use the oscillator because it's a great, you know, very coherent space, very little photon loss, but you couple it to a sort of a bad qubit, and then the errors on the qubit feed back to the oscillator. And this is the story of quantum error correction codes in general, is that you're trying to get information. That information may be imperfect, but okay, we repeat it, we're okay. But also that there is feedback from the ancillas that we use to measure error information, and that gets back into the code, and that may introduce more errors than it takes away, right? That's the challenge, yeah.
Also more basic questions. So
Yeah.
In general, we by having an error, we can go to some subspaces which are orthogonal.
That's what the error does, yeah.
Here in general, but in this case, we have only one, right?
There's only one error, yes.
So the p kind of detects whether we
Yeah,
have
whether
error
you're,
or not.
right, exactly. It detects whether you had no error or an error, yeah. But you have to be careful, like I said, you have to be careful because there's also, it's not, I made an approximation. I said it's like, you know, you know, I really have not the identity, but there's also this back action that I you know, I can't deal with. The point is that the quantum error correction, or this is what I want to say, I think there's not an easy, I find it's not completely intuitive to understand the quantum error correction fully. I rather write down an equation and check whether it works. Yeah, okay, so that's just, okay, so that's sort of the concluding that the, what I said, a faultless recovery, which you can define for these codes which use few photons and which are fine-tuned to the errors that you have. The problem is that to enact that recovery will be faulty, and it may introduce new errors that your code was not chosen to correct against. Yeah? And so the question then, what you do with these things, you compare and say, and this is also what do the experiments, they say, well, my code, how does it compare with the most basic way of using a bosonic mode as a qubit, which is, vacuum is 0, and, state with 1 photon is 1, and have no error correction. That's the lowest number of photons, so it's, good at sort of, pretty protected, and if my code, performs better than that, then I say, well, and it's maybe helpful. So, and here's, I think, one reason to also keep on thinking about stabilizer codes, because stabilizer codes maybe from surface code, with lots of qubits, very inefficient in some sense. But of course, this overhead actually gives the robustness in principle. But the recovery for stabilizer codes can be simple, or at least there is ways of making this fault tolerant. And there's ways of making easy logical gates. And it's just a formalism that may, well, it's a nice formalism that I think has benefits over sort of taking the quantum error correction conditions and then just sort of defining a recovery, but then saying, well, how the hell am I going to actually implement this in the lab? Okay, yeah.
So in these kind of fault-tolerant architectures, typically these measurements can also be made fault-tolerant.
Yes.
I think what you're arguing is that here this kind of control operator is more difficult to make fault-tolerant.
It's not given. So the point is, what I need to know. So for this code, this measuring the parity is pretty straightforward. But in general, I need to make this, this fault tolerant and this. Okay, so there's several things. I need to do the unitary. Now, for stabilizer codes, this recovery, because this is a projection onto Pauli errors, then this unitary will always be a Pauli. And there are ways of saying, oh, I don't need to do the Pauli in practice. I just write it down on a piece of paper. There was a Pauli error happened. That's beneficial, because then this is not, there's no errors that I get from that. Right? Now, it's much harder for these monotonic codes to say, well, I can write down the unitary, but I know at least for these binomial codes, you do need to do the unitary. It's not like you can kind of write this on a piece of paper and then continue with the code that you've obtained now. No, it's really a worse code then. Right? So you need to do so that's one disadvantage, or the one, one different feature. The other thing is that I think there are ways to do this fault tolerant in principle, but you'd like to have the simplest possible circuits. But yeah, that's not, you'd like to just define this with an answer. It depends. I don't know. That's hard to say. I think you can always make this fault tolerant, I think. But, right now this is a bit abstractly defined. I mean, if you can always map it onto the eigenvalue estimation of some unitary, there's always a way of making it fault tolerant. But it's kind of, gets kind of cumbersome. I mean, there's a difference between doing something in principle and it being practical as a, efficient method. Okay, so any other questions? Yeah.
Is there any criteria, like when your error correction produces less errors than it corrects, and then it's good or not?
Sorry, if you're
Like you said that.
if you have your recovery produces fewer errors, you mean? Yeah, there is sort of what you'd like your recovery to do is to indeed produce only correctable errors, and also, right? I mean, and the point is, yeah, and then that's the problem. Also, is the structure of these codes. It's not, you say I designed a code to correct those errors, but it's very easy for the recovery to then go right beyond, slightly beyond it. For example, do some over rotation, which is like, an A dagger A. So there are codes, like I said, there are codes that can correct, error A to the K. So the error set is sort of like A to the K, A dagger to the L, and A dagger A to the M. So these, yeah.
When you introduce measures of the error, like
Error strengths.
strengths, yeah.
Yeah.
Anyway, can we, like using them, kind of analyze whether it's useful to do correction or not?
Well, I think, yeah, I mean, in principle, yes. And I think in these experimental papers, they also, try to estimate this, to have an error budget of every error, and then see, whether you improve things by doing error correction. And they observe this then. Okay, so let me now switch to stabilizer codes, so at least make a, oh my god, now I don't know where the, oh, it's this word. It's really small. Okay. Stabilizer codes. Okay, so I want to introduce stabilizer codes to you by saying a few things about qubit stabilizer codes, because they are more familiar with that, but also showing that the oscillator stabilizer codes, the continuous variable versions of it, are kind of like, you know, very natural extension. And so the way you choose for the stabilizer codes, the way you choose your code space in this sort of high dimensional space, think about it, n qubits, it's as an eigenspace of a group of unitary operators. And for stabilizer codes of qubits, it's a subgroup of a Pauli group, so tensor products of Paulis. And this abelian group, so every, you know, all these Paulis have to commute, that you call a stable. Otherwise, they don't have a common eigenspace, right? So that subgroup is called the stabilizer. And so, because the code space is that plus one eigenstate, it immediately, of course, suggests that if you measure the eigenvalues of this abelian group of unitary operators, this is the way to detect whether you're mapped into one of these orthogonal spaces, right? So errors, and depending on what error basis you choose, you know, for qubit codes, Pauli errors map you onto these sort of different eigenspaces of this stabilizer. And for oscillators, so if you say, well, I do Paulis or products of Paulis for qubits, what's the analogy for oscillators? Their displacements, right? So if I have 3 oscillators, I have displacements on the first oscillator, the second, and the third. Now this is a continuous group, and I can take a subgroup of that is abelian, and I say I take the plus one eigenspace of that subgroup, and that's a code, right? I can do similar things. Okay, so that's just very roughly. So you can do it also for qdits, but I don't want to talk about this too much. Okay. So what is this Pauli? So we define this formally as so if I have n qubits, I define a Pauli group. And so I write down what generates this group as, you know, single, you know, z on qubit 1 up to z on qubit n, x on qubit 1, x to qubit n. You also have to have some phases, because if you take products of this, you can create I times, you know, I times the identity and so on. And this is the group generate. This is just notation. And so what you do to get the stabilizer, to create an abelian subgroup S out of this Pn, should be such that minus identity is not in this S, because otherwise I can't find a space that has plus one eigenvalue with respect to elements in here. And so formally the code space is defined by all vectors, all n qubit vectors, such that for all elements in this subgroup, S on this vector is itself. And what is very nice about this stabilizer code formulas is that there's sort of an organization of all the elements in this Pauli group. So there are elements that are in S. They are the stabilizers, so they have plus one eigenvalue for the code space. And then there are other elements in P, and they can play the role of logical operators and errors. So I know immediately what the logical operators and errors are. And if I had asked, so there's these binomial codes, and we worked on this to try to say what is the logical operator. Sometimes you can guess this, but it's not coming out of this formalism because there's no sort of underlying group structure. At least it's not so obvious there. Okay, so what's the time now? Just make sure. Oh yeah, so the clock is there. Okay, that's good. Yeah. Okay, but the game has already started, so now. Okay, anyhow. Yeah, so the... okay, so now what I want to... This is a little bit formalism about the doing this for polys. And the reason to do this formalism is that this formalism extends to the to qdits and to displacements very naturally. And if you're familiar with while operators or Heisenberg group, that's what it relates to, but I don't want to get into sort of formalism. So if I have a poly acting on n qubits, then up to a phase, which I ignore, I can write it as something where on the qubit 1 I have either x or z or x and z happen, and I can write that as there is some bits, which is either 0 and 1 that tells me whether I have an x there or not, and the z, which is also some bits. And so I can characterize this poly by a 2n bit string, right? And the first part of this bit string, n bit string, is un, that just tells you whether x is there, and the second part tells you whether there's z's also. And that polys, they commute or they anti-commute, but there's a nice way, concise way of writing this anti-commutation commutation in terms of a symplectic inner product involving these vectors. So I'm not showing this. So okay, so I have P, U, P, V, and I want to know whether they anti-commute, and so it's going to be some -1, +1. And that depends on the symplectic inner product between these vectors. So this is not the usual inner product, but there's this S, which is makes it a symplectic inner product. And here, all these, this type of this is V transpose SU. And if you write it out, it looks like this. So why is it, why V2 with U1? It's because, of course, if I have two of these, the X part of this guy possibly anticommutes with the V part of the other, right? So this is why there's this crossover like this, and the same thing here. And because we do only modulo 2 arithmetic, the fact that this is a minus doesn't really matter. Could also be a plus, right? And this product is just, okay, this is a bit string, so I take, it's just, again, modulo 2 arithmetic, so I just take the inner product of every bit, and then, mod 2 everywhere. Yeah, so now if you have n oscillators, the bit string gets mapped onto a vector u that is not in R to n, right? So here the bit string was in something that's Z to n, right? But now I map it onto R. Okay, so what does that look like? So let me show you explicitly. So I want to define sort of a Pauli equivalent. What's happening with this? Oh, this is dead. Okay, I guess it doesn't work. So we've talked about displacements before. So for a single oscillator, like the Paulis are a basis for on qubit, displacements are an error basis for a single oscillator. And so I could, there's displacement in the P in the Q direction. There's two directions in phase space, and they are sort of, I can associate them as an XA. X now depends, this is sort of the Pauli version, X Pauli version for oscillator, but it depends on a number A, which is in principle an element, a real element. So it looks like this, and that's just the displacement of this. This is just some, taking care of some square root of 2 and so on. And similarly, ZB is something where I have a shift in the other direction, right? If this type of element shifts an eigenstate in Q, right? And this shifts an eigenstate in P. Okay, so then I can look at the commutations ZB XA. What is this this thing? And so when AB is an integer, they commute. And you can see this. Okay, so there are several ways of seeing this. These, You know the rules for displacements, d alpha, d beta, and versus d beta, d alpha. Another thing that you can, as just a little exercise, I think this is a nice thing to realize. You know, if you have any two A and B such that the commutator A and B is proportional to identity, then I can write, you know, there's these Baker-Hamper-Hausdorff, like e to the A times e to the B is e to the A plus B, and then some corrections which depend on the commutator. But if the commutator is identity, this number of corrections stops, right? I don't, you know, if I take the commutator of A with this, it's 0. And that gives you some relation like, you know, e to the A, e to the B, this is equal to this. So that's just a little exercise to show this. Okay, maybe I'm going a little fast with this. Okay, so yeah, no, I think it's actually good that I'm covering some of this. So the so now, okay, so that's just a single oscillator commutation. So now again, I can do that for multiple oscillators. So now I have again a vector, like I said, I have a vector u1, u2, and there are now two vectors in R, so R to the 2n. Sorry, the entries of this vector are elements in R. And so I can write my PU, it's very similar as my Pauli's, an XU1, according to this definition I gave on the previous slide, and an element, you know, Z UN plus 1, etc. This is again up to a phase. And so you can construct again the inner product. If you have two multi-oscillators displacements, you can again look at their commutation, and there is an overall phase factor which depends on the symplectic inner product between these vectors, but these are vectors in R2n now. And now there's a very important point I want to make as a last comment. And I think this is really, I find this conceptually very interesting. So you say, well, when do these commute? So like what I want to do, if for oscillators, I want to again construct an abelian group. So I want to construct a set of PUs that are commuting. So this has to be 1, right? Now how can this be 1? Well, if this inner product is it's some integer, right? In one case, of course, it's, well, 0 mod 1 sounds kind of silly, but it's just an integer. And so one case I can take where this is 0. So I can take a subgroup where all, subgroup of Pauli's, or, these are these generalized Pauli's, where all U and V have 0 symplectic inner product. And I want to make a forceful point that is a completely uninteresting class of codes. So the point is that these are the earliest codes that have been defined. So when the stabilizer code formalism came about, there were people, Brownstein and Lloyd and so on, they defined a continuous variable version of stabilizer codes. So you have a 9-qubit code, and you can have a continuous variable version of a 9-qubit code. So the 9-qubit Shor code encodes a single qubit. The continuous variable version of the 9-qubit code encodes a single oscillator. And the point is that you ask, well, are these codes protecting you against something? And we have now a new result, and this actually is not entirely new, because it follows from results on Gaussian quantum information, or indirectly, is that, well, we have results that if you, for example, a continuous variable version of a toric code, and you do perfect decoding, you're not improving the error model at all. You're actually just squeezing the error model. So you have something where I have a toric code that encodes 2 oscillators. I subject it to Gaussian shift errors, and I look at what the logical error model is, and it's only squeezed, which means that maybe my new oscillator, the encoded oscillator, I have less noise on the P quadrature, but then I'll have more noise on the Q quadrature. So you can't protect quantum information that way, right? You only can protect their classical information. But the point is that this is not the only possibility. It's not I can say more about this, but I think I don't. Well, we can talk about it maybe in the next thing. This choice that this is 0 is not the only possibility, because this only has to be an integer, right? So I think the nice thing about the what? Yeah, so there's another option, and this is what I wanted to demonstrate net, which was introduced by Gottesman, Presswood, Gkp, is so the point is about this continuous variable codes. They encode a continuous amount of information, right? The code space is infinite dimensional. It's a non-local oscillator, and in some sense, not surprisingly, you can't protect a continuous amount of information. Well, I don't know. Maybe it's not so surprising. But the Gkp code, which is a code for a single bosonic mode, like the cat and the binomial code, encodes a qubit in an oscillator, right? And it does that in a by taking these two operators. And in some sense, I think it's a fundamental and very nice insight that P and Q don't commute, but these two operators commute. And that's because there's a modular structure. Because, well, why is that true? Because if I look back, e to the A, e to the B is this times this thing, right? So let's look at what this is. Actually, maybe I didn't write this down. So what is this? Well, okay, so the commutator of this with that, what is it? -1, 4, pi, commutator of P and Q is I, right? So I have something that is e to the I 4 pi, e to the I 4 pi. Well, that's 1, right? So, so the point is that you don't need to have P or some linear combination of the P or the Q, linear combination of Q to be 0, or they have to commute. You can have it sort of, it's just there's modular structure here that you're exploiting. And these codes are non-trivial, and then these codes can, have thresholds and blah, blah, blah. So, okay, so I think I want to stop here, but maybe some questions to end.
So this is just taking the A and B to be like this square root of I something for the previous,
yeah, the A, well, this one. Yeah, or I was a little bit messy. You can, you use this A and B to be, this is square root of 2, and then square root of 2 times square root of 2 is definitely an integer, right? So, but it's not trivial in some sense. I think it's a very nice idea. Okay, questions? Yeah.
You mentioned the continuous version of Torah code is useful. What about the continuous version of higher dimensional Torah code?
Not at all. So we have a very general statement. See the point. Okay, so let me say it differently. If you're used to Gaussian quantum information, so you say, well, what are the code states? They are actually Gaussian states for these continuous variables codes. And if I do Gaussian displacement channel, that's a Gaussian noise channel. And my decoding step, the measurement of the checks in this case is also Gaussian. And then there are no-go results on Gaussian information. But we have a general, well, it's important that this is not yet out, but we have a general result showing that if you follow, you have a perfect encoding step, you have this Gaussian displacement channel, you have a perfect decoding. This is for any continuous variable code, any dimension, anything, and then you look at the effective logical channel, that it's only squeezed compared to the original displacement channel. So it just says that it's not, at least, if I took a topological code where I increase, the distance and so on, the squeezing will depend on the size of the system. But the point is, you get better, more noise for one quadrature, so so more noise for one quadrature, but less noise for the other, so you can't win. So there's no threshold. There's not like the Torah code. You know that if you take the code large enough and the error rate small enough, you'll get your logical error rate will become exponentially small, and you don't have a result like that at all for these codes.
So maybe that's saying it's not a topological phase of matter.
Exactly. It's not a topological phase of matter. Yeah.
I mean, you take the large end limit of the and torque it does.
Yeah, I mean, okay, so yeah, but the point is you can say I take qdits and then I take the large n limit, and that it also, yeah, I can say more. It relates to, well, we do have some work on concatenating the Gkp with the surface code, and some limit when your Gkp error information is noiseless, you're kind of in this limit where everything, when there's no phase transition, and it's, yeah.
By continuous version, does that mean like the degrees of freedom are the two conjugate degrees of freedom both real numbers, or is one like a phase and one an integer?
Good question. There's also, rotor versions. So here I'm using an oscillator with P and Q. And so we don't have a statement about where you start with a rotor with a number and a phase and you try to construct a code. And I have the feeling that it's going to be similar, that one sort of, the n is protected and the phase not. But yeah, we haven't worked this out. Point is that our result is also on applying the Gaussian displacement channel and not another channel, but I do feel it's kind of very general, at least this is what my intuition says. Yeah.
So the stabilizer generators on the last slide for the Gkp Code sensor translation.
Yeah, exactly, yeah.
So the +1 eigenstates
Are infinite.
Have wave functions whose support
Is
unbounded.
exactly, yeah.
Doesn't seem like very
No, right. Yeah, good point. So the only use of these codes is to have a sort of a finite envelope and phase space, and they propose some Gaussian envelope where the bulk of the state is in the middle. So if you do a translation, it's approximately. So you're only approximate eigenstate of these two operators. That's sort of but you can still do stuff, and yeah. So, I mean, I think the criticisms, I don't know, maybe John Press can say this more, but I think, I remember actually, who is it from Verstraete, that Ignacio had said these states are completely unphysical, there was criticism maybe that this was very unphysical or not. Is that incorrect, John?
Nobody told me.
Oh, nobody told you. Well, I had the feeling a little bit that this subject has been a bit dormant, no? Or what?
Well, I mean, clearly it's technologically challenging, but we discussed explicitly in the paper that you have to
The finite.
some envelope
Yeah.
and
Finite squeezing, yeah.
Well, I'm just curious, how large do you need to make the envelopes before the quantum error correction conditions are
Well, it's
approximately satisfied?
right, exactly. So there is the photon number. So so these states can be characterized by some squeezing parameter, as if if you have a squeeze state, there's a delta parameter, and the smaller delta is the more squeezing you have, and the number of. But this is sort of, these states are kind of squeezed in both quadratures because they're an eigenstate of both S. You can say how much am I an eigenstate of SP and how much am I an eigenstate of SQ, and you can translate that as a squeezing. And the n is like what is it? This one minus that. No, I don't actually know. Yeah, it's kind of scales like this. So the more squeezing you have, the more photon numbers. No, the higher your photon number is. But we have now. Well, we have. I mean, this is just a subject under development. I'm trying to push out a paper where we show that, what's the threshold on this if you concatenate it with the surface code in some noise model, and can you reach that? And I think it's not unreasonable, actually. We have an estimate like 8 photons or something, which is not crazy, right? But this is like, there's all kinds of approximations and simplifications. So, yeah. Okay, so I think we should stop there. So next lecture, I want to say a few things about decoding.